Hello students, welcome to Time class. This particular session, we are going to have a discussion of Grignard reactions, which is part of chemistry. Before we begin, I want you all to have a set of papers and pens so that you can note down the things as we move on. So shall we begin? Now, what is this Grignard reagent? Sometimes or originally called Grignard reagent. Now, this Grignard reagent is usually having this as the formula. This is the most familiar formula that a student knows, right? RMgx. This R is what? R is a carbon, right? And this is the metal. So it is a metal carbon bond that we have. So it is an organometallic compound. Organo for the carbon and the metal that we have. So it is an organometallic compound. What is so special about this Grignard reagent and its reactions is that it not only benefits the student who is going to prepare for the board and the entrance exams, because lots of questions will come from the Grignard reagent. It also is useful for the chemist because Grignard reagent is a useful starting material. So it is employed in the preparation of various compounds, various useful compounds. And therefore, Grignard reagent not only benefits the student or is required by the student, it is also required by the industrial chemist. So shall we begin? So Grignard reagent is a very useful reagent, right, making lots of material. So we shall begin with what is the method of preparation. So RMgx is made when Rx, what is R that we will see here, that is already shown here. R could be an alkyl or an aryl. It could be also vinyl. It could be also allyl, right? Any of these things. It is all carbon based. So there is no restriction here. R can be alkyl, aryl. Aryl means the aromatic ring, usually a phenyl, or a vinyl, C double bond C, or an allyl, C double bond C, single bond C. That carbon is sp3 carbon. That is the allyl carbon. So this RMgx formation requires dry ether conditions. This is very, very important. So if dry ether conditions are not employed, which means that there is some amount of moisture, then this reaction will not give us this product. So Grignard reagent cannot be prepared when there is even a small amount of moisture. Why so? That we have to check now. Why is this Grignard reagent formation requiring extremely anhydrous conditions? That we will see now. Before we begin, probably this part, R is the negative portion because we said it is an organometallic. Metal is a positive portion, is it not? It's an electropositive atom that is attached to R. So R becomes negative portion. So when it is a negative portion, it can function as a nucleophile. This is the most important thing that we need to know about a Grignard reagent. A Grignard reagent has got the R as a negative portion and therefore can function as a nucleophile. Now let us look at what are all the different types of reactions that this Grignard reagent undergoes. First is with active hydrogen compounds. Now the answer for this lies here, right? Why is Grignard reagent formation formed only or is happening only under extreme anhydrous conditions? That we will know when we are doing this first one. Second, reaction with carbonyl compounds, aldehydes or ketones. Then with nitriles, C triple bond N. With esters, RCOOR. With acid chlorides, RCOCl. With acid anhydrides, RCOOCOR. With carbon dioxide, and finally with epoxides. Epoxide is a closed ring. It's an ether in a cyclic compound. So it's a cyclic ether. So these are all the reactions that we are going to look at. So once we are through, we will test our knowledge. So shall we begin? The first one with active hydrogen compounds. I have chosen here a few substances whose pKa values are given. pKa of ethane, benzene, cyclohexane. Shall we call these as hydrocarbons? Are they not hydrocarbons? They are hydrocarbons, is it not? And these are the ones that are considered as active hydrogen compounds. Active hydrogen compounds are those which give out H+. And the Grignard reagents R- is going to pick up this H+ to form RH. This is the reaction, right? So when Grignard reagent RMgX is there in the presence of an active hydrogen compound, what is going to happen to it? It is going to convert into RH. So RMgX is not going to remain. So let us look at that. So RMgX, if I take, let us say, water. Where is water? Water is here. I'll write here HOH. I'll put it like this. What is going to happen? This is going to form RH plus MgXOH. So what does this mean? Why is this R picking up this H+? Now HOH is having 15.5 as the pKa. So 15.5 I'll write here. And this RH could represent some hydrocarbon. RH is an hydrocarbon, right? So look at all these values. These values are more than 40. pKa is more than 40. 40 onwards it is it not? So between HOH and the RH, which do you think is more acidic? HOH is more acidic. So when HOH is more acidic, it is going to give us H+, right? When H+ is given out, the R takes up the H+ to form RH. The reverse reaction won't take place because this is a weak acid, that is a strong acid. So weak acid cannot displace a strong acid from its salt. So let us take that this is a salt of strong acid, and this is salt of weak acid, right? So reverse won't happen. So the reaction is running in the forward direction, which means that whenever you have a hydrocarbon, right, and any of the active hydrogen compounds, we find that the hydrocarbon is less acidic because the pKa value is so high, right, that it is easily formed when an active hydrogen compound is treated with RMgX. So not only HOH, also alcohol. We have alcohol, we have ammonia, we have methanamine, we have phenol, acetic acid, picric acid, acetyl acetone. See how low their pKa values are. So they are all active hydrogen compounds, which means that they are acidic when compared to the hydrocarbon product that we get from here. Is that clear? So this is the reason why a Grignard reagent cannot stand the presence of active hydrogen compounds. So whenever you have an active hydrogen compound, the Grignard reagent is going to turn into RH. So this won't remain. So whenever an active hydrogen compound, for example, moisture is having water is an active hydrogen compound. So in the presence of water, the Grignard reagent no longer survives. It turns into RH. So if you want the Grignard reagent to be present, we need to have dry ether conditions. I hope this is clear. So active hydrogen compounds, the Grignard reagent is directly reacting with them, giving the hydrocarbon as a product, corresponding hydrocarbon. Is this clear? So shall we move on to the next reaction, that is with a carbonyl compound. Now with a carbonyl compound, we know that we have C double bond O, part of aldehyde or ketone. So what is this Grignard reagent going to do? RMgX, I'll put it like this. R is the minus portion, which is actually delta minus. We will not have a full charge, partial charge. And this is also a partial delta minus, and this is partial, delta plus and delta minus. So this R is going to attack this positive carbon. So this R is nucleophilic and this carbon is electrophilic, right? The carbonyl carbon is electrophilic and will attract a nucleophile. The moment R hits this carbon, this bond, pi bond, is broken and we are going to have C with the R here and the MgX attached to the O. All these things will happen under dry ether conditions. Now the moment you have this compound, now we can add water. When you add water, what is going to happen? This bond is going to break. On this side you have hydrogen, on that side you have OH. Because O is negative, will take up the H plus, Mg is positive, will take up the OH. So what is this now? This is an alcohol, is it not? So this is an alcohol that is formed. So we have C, OH and R as a product, starting from C double bond O. So let us look at the starting material and the product. If I have started with formaldehyde, that is the first aldehyde, both are hydrogens here, we'll have the same hydrogens here also. So formaldehyde is going to give us what? The OH is there on a carbon which is attached to only one carbon. So this is a 1 degree alcohol. So you get 1 degree alcohol when you start with a formaldehyde or methanol. So methanol gives 1 degree alcohol. Now if I replace this hydrogen, one of the hydrogens, with some R, let us say R. So this is also R. Then this becomes secondary alcohol. So if I have any other aldehyde, it could be also aromatic, right? The R need not be only alkyl, isn't it? That is what we mentioned at the beginning itself. R can be aryl, alkyl, allyl, vinyl, any of. So this becomes what? This becomes a secondary alcohol, isn't it? So any other aldehyde is going to give secondary alcohol. Methanol, that is the first aldehyde, first aliphatic aldehyde, gives 1 degree alcohol. And if I have this also as an R, it is a ketone, is it not? So this is also going to be a ketone. So right here, ketone gives us what? Tertiary alcohol. Clear? So a Grignard reagent, how different compounds it is giving. It can give a 1 degree alcohol when treated with methanol, or a 2 degree alcohol when treated with any other aldehyde, or a 3 degree alcohol when treated with a ketone, right? These are all the things that we understand from the Grignard reagents reaction with carbonyl compounds. Clear? So these are the 3 things that we need to note. So a ketone is going to give 3 degree alcohol, any other aldehyde gives 2 degree alcohol, and the first aldehyde, methanol, which is aliphatic, gives us 1 degree alcohol, right? The initial condition is to be maintained, dry ether, followed by water. Clear? Shall we move on to the next reaction? I hope this is clear. This is with nitrile. Nitrile means what? Nitrile means C triple bond N, isn't it? So you start with a C triple bond N and then write the RMGX once again. And this is the delta plus, this is a delta minus. And this we know is delta minus and that is delta plus. So the R is going to attack the carbon and this pi bond will break. And what are we going to get? We're going to get C with an R attached there, double bond N, and the N will have the MgX attached. Now this is again under dry ether conditions. Then upon hydrolysis, what is this going to give? This bond is going to break completely. OH, H, OH, H. So this is removed as NH2MgX and this part becomes a gem diol. Gem diol will lose a water molecule and will form a carbonyl compound. So this OH and OH, one water molecule is lost because gem diols are not stable. So if you have started with some RCN, we'd have a RCOR. So this is a ketone. So a nitrile is going to turn into a ketone. It could be aromatic or aliphatic, not going to matter. So you're going to get a ketone here. That ketone, if you still have some amount of RMGX left, means this RMGX is in excess, let us say, or 2 equivalents, you're going to get a 3-degree alcohol, right? Continuation of what we saw in this here. So the same thing will happen. So it is nitrile to ketone to a tertiary alcohol. That sequence we need to know. We need to internalize and then use when the opportunity strikes. Yes. So shall we move on to the next question? Next reaction rather. With esters. So with esters, we are going to take up the formula of an ester as R C double bond O OR and then RMGX once again, the Grignard reagent, and this is the delta plus and this is the delta minus. So this delta minus is going to attack the delta plus here, nucleophilic attack, and this OR is lost. OR is a good leaving group, as you will see now. Between acid derivatives, acid chloride has the maximum, what shall we say, reaction with a nucleophile. So acid chlorides followed by acid anhydrides followed by esters, they can react with a nucleophile, undergo a nucleophilic substitution. So what is going to happen? You're going to have R C double bond O R. So this is a ketone now. So when we started with an ester, we get a ketone, and that ketone will give tertiary alcohol. The initial reaction is in dry ether, right? And then when you get this tertiary alcohol, we bring the H2O there. Actually, when this happens, the single bond doesn't break so easily. The pi bond first is broken, and when this back polarizes, then the OR is out. So OR will not be out in the first step itself. It is a pi bond that breaks. Whenever this R attacks this carbon and carbonyl carbon, the pi bond, which is the weaker bond, that will break, right? But when it back polarizes, but that is when O minus becomes O, that is neutral O again, then the OR will be lost. Ultimately, what is lost is OR. So OR is lost and we get ketone. Once you get the ketone, you get a tertiary alcohol. So this is also ester to a ketone to a tertiary alcohol. Nitrile also gives the same thing, is it not? So esters will also give the same thing. Now, as I mentioned, RCOCl, it is good to note here itself, RCO OCOR, anhydride, and then RCOOR, that is what we did now, ester. These are all in this order. That is, the Cl can be easily removed, followed by this OCOR, followed by this OR. Clear? So this is the order of reactivity with a nucleophile. So nucleophilic substitution order. What is the nucleophile here? Nucleophile is the R, right? So the R is going to replace this Cl, replace this OCOR, replace this OR. Clear? All these things are nucleophilic substitutions. Clear? And ketone to tertiary alcohol is an addition. It's a nucleophilic addition, because in the tertiary alcohol, we do not have any pi bond. So till this point, there is a pi bond, so it is a substitution. But ketone to tertiary alcohol is a nucleophilic addition. I hope this is clear. Next, we'll move on to reaction with acid chlorides, which we have seen already, right, is part of the same nucleophilic substitution. And in fact, acid chloride is better than ester. So for the sake of completion, we are putting it here. So R is going to attack, the Cl is going to be out, you get a ketone. So RCOR. If you find that all are R's, right, and it may mislead, right, to us that all R's need to be the same, need not be. So if that is the case, I'll put an R1 here and an R2 here. So this is the R1 there and that is the R2 there. I think this should be good. Then this will turn into a tertiary alcohol, because the moment you get a ketone, if you have this RMGX is in excess, then you're going to have a tertiary alcohol formed. So acid chloride to ketone to tertiary alcohol. Again, So how many cases you find ketone being formed in the first step, and then second step is the old one that we have seen already, ketone to tertiary alcohol. Clear? Next, acid anhydride. Again, for the sake of completion, I am doing it here, though you already know it. So R C double bond O, O C double bond O, and then R, and then RMgX. Again, this R is going to hit this carbonyl carbon, and this RCO minus is out. So you get again a ketone, again a ketone, again a tertiary alcohol. Clear? Next, with CO2, carbon dioxide is also going to react with RMgX. So I can put this carbon dioxide like this, put the RMgX and use this R. So what I have shown here is that R takes up the 2 electrons of the bond. Only then it becomes R minus and hits this carbon. And then this pi bond breaks. And you're going to have R, C, O minus. That O minus will become OMgX. So it is double bond O here. So I'll put here MgX. Up to this it is dry ether. And then hydrolysis. HOH. So you get RCOOH. One interesting thing to note here is that suppose we have this RCOOH present and you still have RMgX around. What is going to happen? This is an active hydrogen compound and the first reaction takes place. I want you to note that. In one of the questions we are going to encounter this. So if RMgX is around, right, you are going to have RCOOH reacting with RMgX. So you have to take calculated quantities of RMgX. You should not have excess of RMgX. If it is there, then it is going to react with the product itself, right? So that should not happen. So if you are particular in forming the carboxylic acid and not getting any other byproducts, you should take calculated quantities of RMgX for how much CO2, how much of RMgX has to be taken up. Clear? Next, we'll move on to epoxide. This is the last reaction that we said we are going to do. Now, epoxide is a cyclic ether, we said. So the RMgX, I'll put it here for the sake of clarity. This R minus is going to attack this carbon and this bond will break. If I take this as carbon number 1 and that is carbon number 2, the R is directly attached to carbon number 1. Then we have the carbon number 2. Then we have the OMgX formed. That OMgX will ultimately turn into OH upon hydrolysis. So you get a primary alcohol. So RCH2, CH2, OH. You get a primary alcohol. With an epoxide, you are going to get a primary alcohol. Now let us say that you have an epoxide of this kind, where there is an R attached and we have the RMgX going to react. Now where does this R go? See, this is sterically hindered compared to this carbon because here you have only hydrogens. There is hydrogen no doubt, but there is also an R. So it is sterically hindered. So steric hindrance is there in that, on that carbon. So the R is going to attack this carbon and this O is going to go. So you have R, CH2, then CH with an R and then OH ultimately. So here what do we find? We find that this OH is there on a carbon which is already having a carbon. So you get a 2-degree alcohol here. Here. So wherever the steric hindrance is there, the R is not going to go. So the nucleophile has to go and attack. So it should find a clear path. The path needs to be clear there. So, two hydrogens do not offer as much block as one hydrogen and one R, or when two hydrogens or when two R's are there, the problem is even more severe then. So, steric hindrance will see to it that the R doesn't go to that part. So, these two things we need to note. So, steric hindrance is a very important thing that we need to know when we are dealing with formation of or reaction of Grignard reagent with epoxides. I hope this is clear. So, now are we in a position to take questions? Yes. The very first question, reaction of Grignard reagent C2H5 MgBr with C8H8O followed by hydrolysis gives a compound A which reacts instantly with Lucas reagent. So, we know that this is going to be a tertiary alcohol, right? We know that the tertiary alcohol will immediately turn into a tertiary halide. Tertiary alcohols are very reactive, is it not? So, this will give us instant reaction with Lucas reagent. Lucas reagent is what? Concentrated HCl and zinc chloride anhydrous combination. So, we need to have a tertiary alcohol, and the tertiary alcohol will form a tertiary alkyl halide. Now, this is C2H5, that is the R portion of the Grignard reagent, and this is C8H8O, and look at how many carbons are there, 10 carbons are there, 2 from here and 8 from there, 5 hydrogens and 8 hydrogens, so 13 hydrogens there, clear, and then a Cl there. So, here what we find is, we have options here, so let us look at the options. Now, where is the tertiary alkyl halide? This is primary. This carbon is attached to only one carbon. This carbon is also primary. This is primary. This is also primary. What about this? This carbon is attached to a carbon here, a carbon there, and a carbon there. So, it is tertiary there. So, this is the one that is going to be the product. So, this carbon is having only one carbon here and one carbon there. So, it is 2-degree carbon. So, this is the answer now. So, let us look at the starting material, what it would have been. So, benzene ring, I will put with the circle there. Then C, then the C2H5, that is a C2H5 there. And wherever the Cl was there, it was OH. And now we have a CH3. Clear? So, Grignard reagent formed this. And this on treatment with Lucas gave that with a 3-degree alcohol, and you got the turbidity there. Now, before the Grignard reagent came in, what was the carbonyl compound that we have? It was this, because from the Grignard reagent we got the C2H5. The C2H5 attacked here. So, I will put the C2H5 here, MgBr, which attacked this carbonyl carbon, and that became OH, that is the OH here. And this is C2H5 that you have here, and the CH3 continues. Clear? So, acetophenone was the starting material. Look at how many carbons are there. 8 carbons are there. Hydrogens 3, 4, 5, 6, 7, 8. Yes. So, C8H8O it is. Clear? So, we have tracked. We have got C8H8O. Clear? So, the compound B is option C. I hope this is clear. We'll move on to the next question then. Now, this is the simplest, I think. Grignard reagent shows addition on all these, wherever there is a pi bond. So, there is a carbon which is delta plus, delta plus, delta plus, and there is a pi bond which can polarize, right? All of these. Simplest question. Now, what is the product that you get in the first step when you have excess of magnesium in dry ether? So, I will write the starting material. With the skeleton part I will write. There is a Br here, C, then C, there is a Br, and then there is a C. When you say there is excess of magnesium, magnesium can attack both the carbons, right? So, wherever the Br is there, the Mg is going to be getting inserted in that. So we'll insert the magnesium here and here. So what do we get? MgBr and then MgBr. This is the first step, right? They don't happen one after the other. They are one step. As long as you have sufficient amount of magnesium, one magnesium will come to this part, one magnesium will go to that part, right? And form the Grignard reagent. So there are two RMgX formed. This is the RMgX, RMgX. Clear? So this is ether, diethyl ether. Diethyl ether is usually the ether that we use as the medium, right? Which will not have water. So dry ether, when you say dry ether, it means that it is diethyl ether without water. I hope this is clear. Next question. Now here we have been given 4 options here. The aldehydes which will not form Grignard reagent with just one equivalent of Grignard reagent. Now there is only one carbonyl group here. So one RMgX is sufficient for this. There is one carbonyl group here. So one RMgX will be sufficient for this. But then look at this part. There is a carboxylic acid. So this is the active hydrogen compound. So one more RMgX is used here. So here 2 equivalents. Here it is 1 equivalent. And look at this. This requires 1 RMgX, no doubt. And this part doesn't react with that because it is only an ether there. So this is 1 equivalent. Look at this. Again 1 RMgX required here. And then here again you have active hydrogen compound. It's an alcohol. We know that alcohol has got 16 to 19 as the pKa. So this is again 1 more RMgX required here. So this also requires 2 equivalents. So B and D require 2 equivalents, not just 1 equivalent. So B and D or option 2 is the answer. I hope this is clear. So A and C require only 1 equivalent of the RMgX. Next question. Now this cannot be prepared by. Now what are 1, 2, 3 and 4? Are they all carbonyl compounds? Yes, they are carbonyl compounds. So let us check. The first one is C double bond O, H and H. What does the Grignard reagent do? Will bring one R and that is going to become OH, is it not? So take this Grignard reagents R. In addition to that, there are 2 hydrogens required. Are there 2 hydrogens here? There are no hydrogens here. So it cannot be 1. Look at 2. I need to take another pen here because the background is requiring it. So a pH and a CH2CH3 and a CH3 are present here. pH, a CH2CH3 and a CH3. Yes, so 2 is okay. What about the third one? There is a pH, there is a CH3, there is a CH3CH2. That is what you required. A pH, a CH3 and a CH2CH3. So 3 is also okay. What about the third one, fourth one? You have a CH3CH2, you have a CH3 and you've got a pH. So another combination. So 2, 3 and 4 can give this product because they have the starting, right, groups and the group coming from the Grignard reagent. Whereas 1 has got 2 hydrogens which are not there in the product. So 1 is not going to give us the product. Clear? The order of reactivity, I think this is one of the simplest questions. Once again, you know that this X needs to be a good leaving group. So leaving group is iodine more than bromine more than chlorine. So we have option A as the answer. Clear? So leaving group is also a very important thing because the RX bond needs to break to accommodate the Mg. Therefore, to break, you need a good leaving group. Clear? Next, now look at this. There is a Br here, there is a Br here. I think it's a symmetrical molecule. C triple bond C, on either side CH2Br, CH2Br. With excess of Mg in dry ether, this part is also getting an insertion of magnesium, even that part. But what if only one equivalent of magnesium is given in dry ether? That we need to check now. Look at this now. Now we have C, C, triple bond C, single bond C. On either side you have a bromine there. Now only one equivalent of magnesium is there, so only one Mg will get inserted. The other bromine will remain as it is. The moment this is formed, you know that the molecule is not a straight molecule. Though it is a straight chain, you have a bend at every carbon, right? For example, here there is a 180, there is a 180, and here there is an angle there, tetrahedral angle, here a tetrahedral angle. So this is the R, which is delta minus. It can undergo an internal nucleophilic substitution and the Br is out. So what will form? This MgBr and that Br will go out as MgBr2. So what is left now? C triple bond C, a carbon, and a bond. This should form now. In fact, this is there in option B, cyclobutane. But then in cyclobutane, look at the bond angle. This bond angle is close to 90. Whereas sp requirement is what? It's an sp carbon. Sp requirement is 180 degrees. So this molecule cannot form at all. So before this molecule forms, or if this molecule has been part of an intermediate, let us say, it won't be. Still, if you start with this molecule cannot be in this position. So what should happen? What should happen is that this bond should break and this bond should break. So when it breaks, you get an open chain. So if this is carbon number 1, let us say 1, 2, 3 and 4. You have 1, 2, 3 and 4. On the first carbon, between the first and the second, you have a double bond. Between the second and the third, you have a double bond. Between the third and the fourth, you have a double bond. So this is what? This is option D. Is it not? So this is a much more stable substance than this. This is very unstable. It cannot hold the molecule in that position because carbon is sp and you require 180 degrees as a bond angle, whereas you have close to 90 degrees. So this molecule won't be formed at all. So instead, you will get the open chain form. So this is what? How do you name this? Buta 1, 2, 3 triene. Clear? So it is option D. Now, which of the following reagents will react with Grignard reagent to form an alkane? So which of these is an active hydrogen compound? That is what we need to know. Active hydrogen compound means it should have a very low pKa value. Now nitroethane is CCNO2, which means that this hydrogen could have gone and you get a minus charge there. Acetyl acetone is C double bond O, a CH2, a C double bond O and a C. So you'll have a minus charge here. Acetaldehyde C double bond O, H. So you'll have a minus charge there. And the fourth one is acetone C double bond O, a C, and you could have a minus charge there. Which minus charge is stabilized? That we need to understand. That will give a parent substance with low pKa. Now this minus can be delocalized into the NO2. NO2 is an electron withdrawing group, no doubt. But what about this? This can be delocalized either this side or even that side. In fact, this has got a pKa of 9 we saw in that table, is it not? So it is acetyl acetone that has the minimum pKa and can react with Grignard reagent to form an alkane. Clear? So it cannot be acetone. Acetone also has an electron withdrawing group in the form of C double bond O. Also for acetaldehyde there is, but for acetyl acetone, right, the delocalization is on either side. So the minor charge can be easily delocalized and therefore can get stabilized. And therefore B is the parent substance whose pK is so low that it can be the active hydrogen compound to the Grignard reagent. I hope this is clear. Next, how many liters of ethene would be produced when 2.62 grams of vinyl magnesium bromide? Vinyl magnesium bromide. So there is a hydrogen there and there are two hydrogens there. Is going to react with what? Ethine. Ethine is the active hydrogen compound. So this part is going to take up this part to form ethene. C double bond C, H, H, H and H. Clear? Now look at how many grams do you have? 2.62 grams. Now you get the moles. To get the moles, what do we need? Weight by molecular weight we need to do. 2 carbons, 24. Magnesium, 1 magnesium, 24. 3 hydrogens, 3. Bromine, 80. Add up. 8 plus 3, 11, 9, 10, 11, 12, 13 by 131. So this is nothing but 0.02. And then how much of ethane do you have? 224 ml at STP means divided by 22,400. So this is 0.01. So 1 mole of this and 1 mole of this would give 1 mole of this. But then this is 0.02, this is 0.01. So which is limiting? This is the limiting reagent. That is excess, is it not? So use of excess and limiting reactants also is being employed here. So the limiting one is going to decide how much of product is going to form. So 1 mole will give 1 mole. So 0.01 will give you 0.01. So 0.01 is the number of moles of ethene that you get. So into 22.4 would be the volume that you will get. So 0.224, where it is? Option A. Clear? So this is a numerical based on Grignard reagent. Yes, a different kind of question. So we are trying to cover as many different questions as possible so that you will not face any difficulty when you are actually writing the exam. Clear? Next, I think this is the simplest of all. Now, this phenol has got a pK of 10 and is a Grignard reagent. So this is the R of that. R of that will take the hydrogen of this to form benzene. That's it. So this is active hydrogen compound. Active hydrogen compound will give the hydrogen there and this R part will pick the hydrogen to form the hydrocarbon, benzene. Clear? One more question on this carbonyl. Where is this 3-degree alcohol formed? Now this is the R which will attack this C. The Cl is a good leaving group, will go out, right? So what do we get? We get the R, then the C double bond O, then the hydrogen, right? And because this is excess, you will have R, C, OH, H and then that R. This carbon is attached to only 2 carbons, so it is 2-degree alcohol. It is not 3-degree alcohol. So A is out. Now this will give us, because acid chloride we saw with Grignard reagent will immediately give the ketone and ketone will turn into a tertiary alcohol. Again acid anhydride, so this will go out, that will go out there. Again you will get a ketone and from ketone you get a tertiary alcohol because this is again in excess. And then this is CH3 going to attack the C. It is not the Cl that goes out, sorry, it is not the OAT that goes out, it is a Cl that goes out because we saw acid chloride more than acid ester, is it not? So what do we get? So CH3, C double bond O, OET. Again you got an ester. So from the ester, you get a ketone. From the ketone, again you get a tertiary alcohol because you have not been given that it is 2 equivalents or 3 equivalents, it is an excess. So B will give, C will give, D will give, only A doesn't give. A gives a 2-degree alcohol. I hope this is clear. Next, look at this, which is a good leaving group. Good leaving group is bromine. So Mg will get inserted here. The moment you get Mg there, the next is reaction with active hydrogen compound. Instead of active hydrogen, it is active deuterium compound. So wherever the MgBr is there, that is going to become D. Option A. The Cl will be left, right? The Cl cannot go. Bromine cannot be there and Cl cannot go. So option A it is. Clear? D2O is heavy water. So instead of H2O, the pK is slightly higher than that of water, but still well within the range. It is definitely better than a hydrocarbon. Next, there are some compounds shown here. You have to check how many equivalents of RMGX are required. This is an ester. Ester to ketone to tertiary alcohol. You require 2 moles of Grignard reagent. Acid chloride to ketone to tertiary alcohol. 2 is okay. This is ester to ketone to 3-degree alcohol, and there is also an active hydrogen there. We mentioned that in the questions we are going to take up this active hydrogen usage there, active hydrogen compounds usage there. So this part is taking 2 moles and that part will take 1 mole. So this is true. And here 1 mole, 2 moles and 1 mole. This is active hydrogen compound. This is an aldehyde. This is an ester. Ester will require 2. Aldehyde will require 1. Active hydrogen compound will require 1. So this is 4. 4 is true. Incorrect option is A. For A you require 2, not 1. I hope this is clear. Order of reactivity. We know that a Grignard reagent is having R as a minus portion, which is nucleophilic, and it is going to attack a carbon which is electrophilic. So this carbon will have some inductive effect and is therefore less positive compared to the previous one. This carbon is having 2 methyl groups giving, still less positive. And this is giving, this is tertiary butyl, gives more inductive effect. And sterically, 1 is the best. So sterically and electronically, if you're looking at 1 is greater than 2 is greater than 3 is greater than 4. 4 has least positive charge and maximum steric hindrance. Here maximum positive charge, minimum steric hindrance. Correct? That is how A is the answer. Clear? I hope you have taken up sufficient questions to test your knowledge. One more, I think this is very similar to what we did in the previous one. So the Grignard reagent is going to attack a carbonyl compound. All are carbonyl compounds, B, C, A, D, all these things are. Now what you require is Me, Et, pH combination. You have Me, Et, pH combination. We have Me, Et, pH combination. We have Me, Et, pH combination. We have, there is no Me. We have Et, pH combination. So this will not give. So A, B and C will give this product. D will not give because D will form what? 2 ethyls and 1 phenyls on the COH. Clear? I think this is the last question that we'll be doing. 2-bromo-octane. Let us put this 1, 2, 3, 4, 5, 6, 7 and 8. 2-bromo. There is a hydrogen there. And Mg will get inserted there. And this is going to react with carbon dioxide. The moment this happens, actually this bond breaks and you get a radical. The moment you get a radical, the chiral carbon can be of 2 kinds. The hydrogen can be down or hydrogen can be up. So you have both the products formed. So A and B. See what is A? Look at this. This is 1 in the RS configuration. 1. This is 2 this is 3 and that is 4. Hydrogen is on the vertical line, so on the right position. 1 to 2 to 3 is anti-clockwise, so S. This is 1, that is 2, this is 3. This is R. So you get both R and S. C. Because here the carbon forms a radical. Once it forms a radical, there are 2 cases. So 2 chiral carbons can form. Clear? So that is all for this session. I hope you had sufficient theory covered, sufficient problems taken up, right? And you have tested your knowledge sufficiently on different types of questions, right? So see to it that you make the most of these sessions. You can note our details here, right? The YouTube channel, which will have live sessions as well as short videos of this type for all interesting videos, right? And for any knowledge based things that can assist you in your entrance exams, please subscribe to us, right? And see to it that you make us part of your successful journey. Thank you. Best wishes.